So today will be the second part of the cohort study. So I'm going to pay more attention about how to apply the data from cohort studies and show you the examples about how to do perform indirect or direct standardization as the first step to describe what's going on between the comparison groups. First of all, let me show you some interesting pictures. Do you see? It looks like pretty apparent and straightforward, right? So a car just hit the electric pole and then flip over there. So is this causal? Car is the cause and the outcome is like that. Is that true? With such a snapshot? Maybe, but even if it's so apparent, it could be something arranged by people for movie maker, for example. Or unless we could have the information about the films in different angles, right? And see what's going on. We see the car move to the pole and then lose control and then hit the, and then blah, blah, blah. This is cohort study, right? But if what I can see is here, it's something like that. It happened. So the only thing you can do is to ask the driver, but the driver might be dead or something, and maybe no witness at all, right? So if you want to perform a retrospective one, the information might not be so reliable, right? But if you could have information for everything, like the records from the monitoring thing in the car, or the information from the police records, or even films from the car behind it, then we could have a much better evidence about what happened here, right? So this is a good example about the judgment of a causal relationship. Another thing could happen by chance, like this. It's a rainbow behind it, and there's what's that, thunder? Yeah, so they fit exactly. If we try to perform any kind of statistical analysis, it will be definitely significant, right? But without background information or knowledge about the cause of lightning or the cause of rainbow, we might think that, there must be something going on to make them happen together, right? And which could be causal. Might be controlled by a goddess or something. Goddess rainbow. She is fighting with a god of something, something, something. Anyway, you could make a lot of story about that. Or, are you seeing an angel here? Angel. Or angel. Something happened by chance, right? But you cannot jump into the final conclusion with a single snapshot about the causal relationship. Okay, outline. So I'm going to revisit the idea about mortality. But actually, everything I'm talking about today is also applicable to morbidity, especially for direct indirect standardization. It works for mortality and also for morbidity. And now we're going to review or remind you the definition of the general mortality and cause-specific mortality. And then I'm going to show you how to perform age and gender-specific mortality rate for the calculation of the adjustment for age structure by standardization. And the so-called direct and indirect methods. Direct means that using the way of standardization, the outcome will be comparable from each other. But with indirect, we could only compare the information or the rates from the target population to the standard population only. We cannot compare to all the other indirect standardization analysis outcome. Okay. And then I'm going to introduce the method called Lifetable for the performance or the generation of life expectancy at birth, which is an indicator specifically developed for general mortality, or all-cause mortality only. General mortality, and sometimes we call it all-cause mortality, they mean exactly the same. But if you're writing an article, please unify the terms in your article. Don't put it the general mortality somewhere, and the other parts you use all-cause mortality. Although they mean the same, but don't mix up in one article. But for the study about etiology, we prefer to use the cause-specific mortality. Then we could identify the exact cause of the mortality for a specific disease or specific group of disease. Because if you look at all-cause mortality, then there's an issue about the composition. of the different various causes of diseases, right? But if you focus on cause-specific mortality, there will be more possible to find out the exact causal relationship. So cancer mortality will be an example, but you could divide them into different kind of specific type of cancer. So even in each kind of cancer, you could specify in different pathological type or molecular type of cancer. Okay, and also TB mortality will be another example. So it'll be specifically talking about the mortality caused by TB, which is generally recorded as the underlying cause of death in the death certificates. That's the rule for almost everywhere in the world. Okay, so when we are trying to perform the comparison for general mortality, standardization will be the most useful and most widely accepted one for the adjustment for age and gender structure. And of course, if possible, we could also perform the adjustment for ethnicity or other demographics. But to rely on the information available from the standard population, right? In the target population or the population we're performing our study, we could do the measurement we want, right? Or try to collect the information from the target population as wish. If we need the age, we need gender, we need occupation, blah, 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 we could have everything, right? But you need to have the same information from the standard population to do the standardization. So that's why one of the limitations of our standardization is the availability of the information from the standard population. Okay. And life expectancy at birth is an alternative way of showing general mortality in a single index. Now, standardization, what we can have is a relative risk estimation, right? SIR, SRR, or SMR. SMR, standard mortality ratio, that's all relative risk estimations, right? Single indication. But here, life expectancy at birth is also a single indication. It's a single number. But first of all, I have to define the terms. Study population or so-called target population. Both of them make sense to me. But in social science, people might prefer to use target population. But in epidemiology or medicine or public health, we might use a study population more. But they mean the same thing. They are your study cohort. They are the cohort you are working on for your research. Okay. And standard population or so-called reference population, both of them are pretty widely used for people from different disciplines. So generally, standard population will be the national or world population in a specific year. Or at least that has to be the population like in a city, like Taipei City or New York City, London, or something like that. It has to be something, generally it should be something much bigger than the study population. There could be hundreds or thousands of people in the study population, but generally speaking, you need to have millions of people in a standard population. Because the purpose of indirect standardization is to compare a smaller group to the general population to provide a stable estimation of the age and gender specific mortality or incidence rates. Okay, that's one of the purposes. So that's why we need to have a standard population which is much bigger, which is considered to be more stable. So we need to do the adjustment for age and gender distribution for the study population by age and gender specific mortality rate, like what we did here. This is age specific one, right? So we combine the genders here. So if you want to split them into age and gender specific mortality rates, then as an example here, we have 3 stratum, right? But if you want to do age and gender specific, then we have 6 strata. There will be 6 strata. We double the number of the strata here. With the direct standardization, we are applying standard populations weights to study populations mortality rates in strata. In other words, we use the percentage of the each age and gender groups in the standard population for the calculation. In contrast, we use indirect standardization to do the calculation applying study populations weights to standard populations rates in strata. So it's the other way around. Similar calculation, but different material for different purposes. Okay, here's an example for direct standardization. So if you have the information about country A and country B, so roughly speaking, what we found, both of them are kind of middle-sized country, 9 million, about 70 million population, okay, about mid-size in the world, like maybe, I don't know, maybe median, the ranking, the population, maybe 50 or 70, country A and country B. Okay, and since the information about age structure has been shown, what do you find there? In country A, most of people are in this age group, over 65, or more than 2.5 million of people in this country. And in this country, there are more people here, age 5 to 19. And the second, the second one will be the age group of 20 to 44, right? So roughly speaking, we have the idea that the age structure is much older for country A, right? So if we just perform the calculation of the crude mortality rate in country A, we could find out that the mortality rate, the crude one, was 1,471 per 100,000. And for country B, it's 414 per 100,000. Yeah? So without the consideration of age structure, it's much higher for country A. Right? But people might argue that country A is much older, so it's not a fair comparison. So we have to do some calculation to do the adjustment for age structure. So country A, country B. So we have to do the calculation with US census population as the standard population here. Okay, and the rate is from the previous slides. If we do the calculation that 74 divided by 49602, that's the age-specific rate for the age group younger than 5 for country A, and they do the calculation for every stratum, and do exactly the same thing for country B. Then you get the information here. Okay, because it's a direct standardization, so to apply the structure from the standard population. No matter for indirect or direct standardization, we have to specify a standard population and give the information necessary for the calculation. Okay, so for country A, for this stratum, it would be 149 times 0.07, which is the percentage of the population. Or you could just times this and divide it by the total number here. Okay, and add up 712. Okay, and then you could do exactly the same thing for country B, 829. So after the age adjustment by direct standardization, actually they're about the same. And even the country A a little bit lower than country B. Okay, so the SIR is a little bit lower than 1. Okay, which is totally different from what we saw in the crude estimation of the mortality rate ratio. Right? It's more than 3 times. Right? But actually they're about the same if we perform the adjustment for age structure by direct standardization. And here comes the other example about indirect standardization. Okay, and this is a real data from the group of male miners back to 1950s. I believe that up to now most of the miners are males, unfortunately. Okay, so gender has been controlled by the study design, right? So we don't need to worry about the confounding from gender. But age is still an issue here. So now we look at the information of the age structure for minors from 20 to 24 and 50 to 59. Ignore the age group older than 60. Okay, so just have a couple of 100,000 people here. Okay. And one of the purposes of indirect standardization is to compare a study group or study population to the general population. And we do need to have the information about the age-specific rates from the standard population. That is so-called indirect standardization, right? Okay, so we use the first column times the second column. The second column, you have to pay attention to the units there. It's the death rate per 100,000. So we have to divide 100,000 after the calculation there for column 3. So 74,598 times 12.26 divided by 100,000. You will get 9.14. That's the expected number of deaths for the youngest age group, right? And you can do exactly the same thing for all the other stratum, and then do the sum up. You could get the expected number of people die. So in other words, if this group of minors die in exactly the same way in the general population, then what do we expect? 181 people. Okay, but that's what exact number we observed during the follow-up. 10, 20, 22, blah, blah, blah. So in exact the same period of time, actually, there were 436 deaths happened in this group of people. So it's pretty straightforward, right? If we use the 436 divided by expected one, which is the number what's supposed to happen if they have exact the same age-specific mortality rate in the general population, then the standardized mortality ratio is 2.41 or 241%, more than two-folds. So we can make the conclusion that in 1950, minors died of TB, so it's TB, for 2.41 times as often as their counterparts in the general population with age adjusted. So when you're trying to make the conclusion, no matter for direct standardization or indirect standardization, you have to specify the standard population. Okay, here is the general population in USA, right? And also you have to specify what had been adjusted. Generally speaking, it will be age and gender, but here is only age. Okay, so this would be something very straightforward again. So now, let's make some illustration about how to explain of standardization. For direct standardization, we are using the weight from the standard population to do the calculation. Advantage for direct standardization is that the information, the outcome is comparable across studies or internationally. So that's what we do for the cancer incidence rate, for the purpose of comparing to all the other countries in the world. But we have to apply exact the same standard population, which should be given by the WHO every 10 years. So you could easily find the world population structure given by the WHO every 10 years. So now we are supposed to use the year 2020 world population as the standard population for the calculation of direct incidence or mortality for any study population. For indirect standardization, using each study supplies its own set of weights for its age and gender structure. In other words, the structure is from the study population on your own, of your own research. So actually it's not so straightforward, or it's not really adjusting age structure. So it only makes sense to compare the study population or target population to the standard population. You cannot compare the outcomes or the calculation estimation across studies. So it's not comparable across studies when age and gender distribution differ across study population. Or we could say that they have different study cohorts, so they are not comparable. It only makes sense for your study population to the general population. Okay, exercise. Occupation A, occupation B. So there are two cohorts. Are they different in terms of mortality? And the reference population is there. Okay, so with this kind of information, we could perform crude. The crude rate for A is very straightforward here. 22 divided by the total number, so 0.0037. Okay, what about crude rate B there? Can you do that? Again, it's very straightforward. It's 14 divided by 6,000. So the answer would be 0023. What about SMR, standardized mortality ratio, which is indirect standardization, right? So it should O over E, observed number, is 22, right? And how are we going to calculate the expected number? So we need to have the information from the reference population or standard population for the rates. So it just use the structure from occupation A, which is 1,000, 5,000, to experience exact the same thing for the reference population, 0.01, 0.003. So you could get the expected number of deaths. Then you could come up with 1.38. Okay, so I'll give you 2 minutes to do the calculation for occupation B for indirect standardization. Okay, but the 1.38 here only makes sense when you are comparing to the reference population. Okay, we are not comparing A to B, we are comparing to the reference population. Nowadays, generally it's done by computer, but why we need to learn the process? I just want to have some sense about the process, about what happened there. Then you have more, empirical feeling about what's going on for the adjustment. You could make a better judgment what they're supposed to do for different kind of situation, direct or indirect standardization. So SMR for B, what is the observed number of deaths here? So it's 14, right? 14. Okay, and what is the structure of the occupation B in the first age stratum? 5,000 times the rate from the standard population, 0.01, 0.01, 0.01 plus 1,000 times 0.003. So we get the answer here. It's 5 or 3, so it's 8. Right? So the SMR for B will be 14 divided by 8, which is equal to 1.75. But can we say that 1.75 is higher than 1.38? No, because indirect standardization, so they are not comparable to each other. You cannot say that 1.75. So the mortality rate for occupation B is higher than occupational A. No. You cannot make that kind of conclusion. But it makes sense to compare to the reference population. Okay. What about the direct standardization for occupation A? So now it's the other way around. We are using the rate from your study population and the structure from the standard population here to do the calculation. Okay, so it's a rate from the target population, rate from the target population, and the structure from the standard population. So the answer is 0.0031. Okay, so you have 2 minutes again to do the calculation for occupation B by the method of direct standardization, using the reference population here to provide information about the structure, age structure. So the process will be the same and the number will be exactly the same. So the outcome, the answer will be 0.0031. So in other words, that actually after they adjust for age structure, the mortality rate for occupation A is exactly the same of the occupation B. Although we saw different things from the estimation of SMR, but this is not comparable. These two are not comparable to each other. Okay, so we cannot say that occupation B is more dangerous than occupation A after adjust for age. Okay, actually they are the same. Okay, so up to now you should have a lot of background knowledge which is sufficient for you for the judgment and the process of calculation for direct, indirect standardization. But anything come up with the good things always comes with a limitation. The first one is that no matter for direct standardization or indirect standardization, they are only applicable for controlling categorical variables as confounders. So if it's a continuous variable, we need to use some other methods called modeling. Okay? But if you want to do it with your hands, with bare hands or calculators, then it has to be categorical variable. So in other words, we might need to categorize the age, which is a continuous variable, right, into groups before we could perform any kind of direct or indirect standardization. And because the availability of the information about age and gender structure is generally available from the target population and the standard population, but not always available for the other factors. So the confounders other than age and gender were not considered here, like smoking, which is generally speaking a very important risk factor for a lot of diseases, right? And lifestyle factors like physical activity or diet, drinking, something like that. Generally, it's not available from the standard population, so it's not available for the purpose of standardization. Okay, and it's not intuitive enough, right? I'm spending like 2 or 3 hours talking about direct, indirect standardization and show you how to do it, how to explain it. So it's not so intuitive for everyone, right? You need to learn and you need to know the limitation of the vintage, blah, 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 to make the adjustment. So it's not so straightforward for every single one, especially for the lay persons. And also the meaning, especially for the psychosocial meaning of death, might be different by age. But in the calculation of the direct or indirect standardization, we consider age are exactly the same. But actually it's different, right? Generally, we evaluated death at a younger age is more harmful to the population, right? So that's why people develop an alternative way for the purpose. Okay, but first of all, I have to revisit the idea about a concurrent view or longitudinal view on a study population. Remember in the curve about the liver mortality for a very long-term period of follow-up cohort study. Okay, so it makes more sense with the longitudinal view based on the birth cohort, remember? So it's always going up, which makes more sense because we already know that lung cancer is more related to cumulative exposure by age. Okay, but if we mix up the different people from different age groups, then it might bend down at the older age groups, which is weird and not so straightforward. So that's why we need to apply or develop some more sophisticated statistical method called age, period, cohort, modeling to sort it out. In that way, longitudinal view makes more sense. But if you want to estimate the life expectancy at birth, what is the best way to do it? Ideally, we should follow up a group of people who were born this year and then follow up for more than 100 years to see what happened for every single one. Okay? Before the last one died, you have no idea you cannot estimate the exact number for the life expectancy at birth, right? And no one cannot survive that long, right? You cannot wait to see for all the people die, right? So we have no choice to use the concurrent view to look at the age-specific mortality rate, to make it try to generate a single indicator to show the general health status in a population. Okay, so that's so-called Lifetable. So concurrent view is defined as a relatively short period of observation. For example, 1 year or 5 years for a population. Then we could have information about the age-specific mortality rate, right, for each age stratum. That's so-called concurrent view. And then we just apply those information in a theoretical population with a number of 100,000 people. Okay, we assume that we observe 100,000 people, and they will die in exact the same pattern as what we observe from the concurrent view of the cohort we are observing, from the youngest age group to the oldest age group. Okay, and then just try to mimic or trial calculation to see what experienced by this concurrent cohort. Okay. So then we could generate the information like a life expectancy at birth. The calculation is basically the accumulated person years contributed by the whole cohort divided by 100,000 people in the very beginning. Okay? So people might ask, then what about the age structure? We don't need to care about age structure anymore, right? It's just like a fish fillet. We have taken away the bone. So you could just enjoy the fish, okay, without taking care of the bone. So you don't need to worry about age structure. But generally speaking, the life expectancy at birth will be given by gender. So if you try to look at life expectancy information for every single country, it will be given by gender. Okay, and generally speaking, 99% of the country, you could find that the life expectancy at birth for female is longer, much longer than male. Okay, in Taiwan, the female life expectancy at birth is around 81, 82. For male, it's like 76, 77. Okay, but there's only one exception in the world. Do you know which country? That the life expectancy is higher for male than female. Any idea? It's India. Yeah, there are a lot of reasons about that. Yeah, but you could look into it. And the methodology has been recommended by UK Office for National Statistics. So it's a well-established, commonly accepted mathematical, scientific methods for the comparison of the general mortality among the countries in the world. Okay. Okay, so we use the tool called Lifetable to do the calculation of life expectancy at birth. It's given by gender, and it's a very commonly accepted demographic index for general mortality. So it just summarizes everything, all the age-specific mortality into a single indicator. So it's widely used for the purpose of international comparison. And also the calculation emphasizes the death in early life stages. So if some kind of the cause of death is more likely to happen at an early stage, its impact to the life expectancy will be higher. If we compare the cause of HIV, for example, in the sub-Saharan countries in Africa, you can find out that the country with a higher HIV infection rate in younger kids, the life expectancy will be much lower than the other countries. Okay. And also, if you look into the contribution for prostate cancer for males, life expectancy at birth, you could find it's very minimal. That's because, generally speaking, prostate cancer happens in a very old age, like 70-something or 80-something or even 90-something. Okay, and the data we need to do the calculation of life expectancy at birth are just simply age-specific mortality rates within the defined cohort observed for a certain period of time, and generally it's 1 year, at least 1 year actually. If you just follow up a group of people for 10 days, then maybe it's very hard to do any calculation for life expectancy. So maybe 1 year is a minimum. Okay, so here's a real example from the England and Wales in year 2009. Okay, so in the very beginning, we assume that we have 100,000 people, right, at the top. 100,000 people men or males, okay? And we apply what we observe in the population for the mortality, age-specific mortality rate from age 0 to age 1, which is 526, okay? We use the rate here, age-specific mortality rate, and we got 500. We expect to have 500 blah, blah, blah people died in the first year of their life. And we do exactly the same thing for females. And the survivors of at year 1 will experience what happened for year 1 and 2 and 3, step by step. And in the end, you could check what happened for the year 100. In the end, there's only 1,000 people still alive at age 100. Okay, and do you know what's the mortality rate for the people at the age of 100? 0.339. So if your grandpa is very old, then treat him nicely because the mortality rate is so high, about 1/3 at the age of 100. you can do exactly the same thing for female. And they just add up all the contributed person years divided by 100,000. That's the number we have here, 77.98 for males and 82 for females. Okay, so this is a trial calculation. This is not what really happened for all the people. We just apply the information we observed in 2009 to a population theoretically which does not exist in reality. So 100,000 people die in exactly the same way in the population based on what we observed for that year in the whole country. So every country report or announce their life expectancy at birth as the most roughly the simplest indication about the general health status. Okay, then here comes the example from real studies. So first of all, we need to define a cohort, right? So this is the timeline. The data become available sometime in 2006. So we decided to follow up this group of people from the January 1st of 2007 till the end of the 2009. So anyone who are alive in the period of observation will be at a risk for death, right? Okay, and because we need to define the age, right? Everyone is getting older every single day. No, every second. So how can we define the age for an ongoing cohort? It's a dynamic cohort. People can join in or leave the cohort if he or she die or immigrate to the other country. So we use the midpoint to simplify the scenario. We define the age at the midpoint of the observation period. Okay, and who are those people? They are people diagnosed with severe mental illness, including schizophrenia, bipolar, schizoaffective disorder, and also substance use disorder, depressive episode, or recurrent depressive disorders. So basically depression. And we use the abridged life table. So the detailed one is just split by every single year, right? But here is a abridged one, so 5-year band. And you don't need to do the whole calculation by yourself. You just download it from the London School of Hygiene and Tropical Medicine or anywhere. There are a lot of such a kind of thing available, which is basically an Excel file, like from the Michigan School of Public Health or University of California, Berkeley or somewhere. There's a lot of tools for such kind of thing available anyway. So just simply put the information about the number of people under your observation and the number of deaths during your observation period. And then it just give you the estimation of the life expectancy at birth, straightforward, with 95% confidence interval estimated. Okay, so it's very straightforward. But the issue is that before the age of 15, clinically we don't give the diagnosis of severe mental illness. So we have no choice to apply the information from the general population. We just assume that we have 100 people in that age group, and that's the number of people, expected number of people died during the follow-up period of time. So we just apply the general population. So that's the starting point to make difference after age 15, right? Because that's the starting point that we could give the diagnosis of those mental disorders. So we could do exactly the same thing. And here's the material. In the calculation of life expectancy at birth, what we need is to have the age-specific mortality rate, right? So here's the figure for people with different diagnoses and the age-specific mortality rate. And can you make a conclusion? Pretty hard, right? Maybe the brown column is higher here, and maybe particularly higher for the purple column, and the red column might be higher there, right? So it's hard to make a quick and simple estimation about which group of people experience more severe mortality issues. So that's why we generate the calculation. And also with the same material, we could perform indirect standardization comparing to the UK population, right? So this is what we found with the severe mental illness. If we perform the age and gender standardization by indirect standardization method, it's a little bit above 2. So in other words, this group of people are experiencing more than double the mortality compared to the general population in UK. Okay, and male is even higher compared to the male. Female is compared to female. You cannot say that a male is higher than female because it's indirect standardization here. Okay. So we could do exactly the same thing for substance use disorder. Whew, so high. Compared to the general population, it's more than 4 folds of the risk. Male is lower and female is high. But the number of people, female, with the problem of the substance use disorder might be fewer. So that's why the 95% confidence interval was so wide. But it's still very far away from 1. So statistically significant. Okay, and also for depression. Amazingly or surprisingly, it's not as high as what we thought. It's a little bit higher than 1, but still significant. A little bit higher than the general population. So the substance use disorder might be the worst to make people die earlier, or so-called premature death. Okay, and also we could do the calculation stratified by age stratum from 15 to 44, 45 to 64, and above 65. So it's much higher compared to the same age groups in the general population, more than 4 folds. For the mid-age group, maybe 3. But if we consider the people who are older than 65, we survive with severe mental illness, it's just a little bit higher than 1. Okay, so it's kind of a survival effect, right? If you could live long enough, then at the later stage of your life, it's not very high. It's just a little bit higher than the general population. Okay, and see similar pattern here for substance use disorder and depression. Okay, so here's the outcome for the estimation of life expectancy at birth. Any severe mental illness is 64. And comparing to the national norm, which is the parameter, right, of the country, for male is 77. So the difference will be as huge as pretty gigantic, right? About 13 years less compared to the national norm. And it's even worse for schizophrenia, almost 15.6 years less. Okay, and schizoaffective disorder, about 8 years, 10 years for bipolar. Substance use disorder about 13.5, and for depression is about 10. So it shows a little bit different scenario about as what we can see in the summation of the standardized mortality ratio, because here we emphasize the effect of younger age. The death of younger age will take more serious or taking more impact to the life expectancy at birth. We can see the information given for female. The worst one will be schizoaffective disorder. The life expectancy at birth will be as low as 64, which is about 70.5 years less compared to the general population in UK. Okay, so with the information from Cohort study, we could generate such a kind of straightforward and easy to understand, right? It's understandable for most of the people, right? Even the Prime Minister in the year-end speech, they mentioned my study. This is my study, yeah, and promised to spend more money to take care of the people with the mental illness in UK. Okay, so that's the elucidate the life expectancy as a tool for the purpose of epidemiological research further. So first of all, it has to be applied with a sufficient number of cases recorded. A big cohort. So at least we need to have like a 4,000, 5,000 people to do the calculation of the life expectancy at birth. If you only have 200 people, maybe it's not enough. There's a minimum required number for such kind of calculation. And the other thing is that death is relatively easier. Death is dead for most of the chances. If you see a bunch of bones, and definitely that person is dead, right? And, but sometimes it's difficult, but for most of the chances, it's pretty easy to do the judgment. So death is relatively easier to detect than the other health outcomes. So we use it as a general indicator for the health status in the population. So life expectancy will provide an alternative indicator for general mortality to highlight the premature deaths. So it's very difficult to say that this is a nice country, people with well taken care of in terms of health if they got very low life expectancy at birth, like North Korea, only 50-something, right? Yeah, and in most of the developed country, the life expectancy at birth is above 80s, right? Okay, so it's a simple and straightforward indication. Okay, and it's an indicator to show the impact rather than just effectiveness. So for the estimation of the relative risk is more about effect, but here we are talking about impact. It's more straightforward, although it's not so etiologic, or it's not so epidemiologic, right? But it's something easy to be understood by the public. So that's why it's pretty useful. And we don't need to care about age structure anymore, right? Although we haven't done any adjustment, right? But the backbone has been taken off. And it's very straightforward for policymakers and lay audiences, okay? Especially for the politicians. They are very simple-minded. They just want to have very straightforward number for them to make the decision. Okay, of course, there are some limitations. Because our study is a group of people with a severe mental illness in London, so it's kind of secondary care, healthcare service users only. So we cannot generate the information to the other population in other countries, even if they have the same mental illness. And it's a simple single index by gender. So we don't need to worry about age structure anymore. So you could feel free to do the comparison across population, across countries, but not across gender. Oh, okay, you can do it across gender. So that's why I said that in most of the countries, the female got the higher life expectancy at birth compared to men, right? So you can feel free to do the comparison. But the problem is that it's way too simple. So it simplifies the scenario. So we are not able to explore the causal pathway between the mental disorder to the life expectancy, like a physical or comorbidity as a mediator or effect modifier, right? We did not consider anything about diabetes, for example. We did not consider anything about smoking or hypertension at all, right? So it's just a simple estimation without consideration of other important factors, especially for a confounder or effect modifier. Personal insight. So up to now, I have finished everything I can give you about how to quantify death, how to quantify the frequency of disease. But they are the fundamental thing to public health, any public health study. And then it's very important to make sure that you have performed fair comparisons before you can do any further analysis with sophisticated statistical methods. So that's the fundamental for everything. If you did it wrong in terms of study design, or you did it wrong for the issue about fair comparison, then any, no matter how sophisticated the tool you are going to use doesn't make any sense. So this is very important fundamentals. So right standardization strategy will give you a better conclusion. In other words, we provide a more precise estimation for the comparison of relative risk. And direct standardization, I can give you a tip. If you remember this, you will know how to do it. Okay, the tip is my cohort rates, or your study cohort rates, and others population, which means the population structure from the standard population. And indirect is the other way around. It's O over E, observed number divided by expected number. And the tips is that my cohort population and others rates, or use the rates from the standard population, apply your study cohort structure in the calculation of O over E. So with these two tips, it'll be very easy for you to perform any kind of calculation for standardization. Read my lips. Standardization is generally the first step to analyzing a specific cohort. Okay, that's the reason why you need to pay more attention to focus on this population. If you find a higher standardized incidence ratio or standardized mortality ratio, right? Because they got a higher risk of some kind of disease of interest, or they experience higher mortality. So that's why you need to pay more attention and try to figure out why. What's the reason make them got higher risk of those diseases? right? So it's very fundamental. And the purpose of standardization is to control the confounding from age and structure for the most part. So it will give you a preliminary outcome estimation. And the SNR or SIR, the I here is incidence for disease, M is mortality. It could be general mortality or cause-specific mortality, right? It's an estimation of the relative risk by indirect standardization. SRR is a method for direct standardization, right? And the purpose of it is to perform the comparison across countries or across studies for international comparison. And all of them are the estimation for relative risk. Okay, that's why I emphasize the idea of relative risk in the third lecture. Remember? Okay, so only direct standardization outcomes are comparable across studies because they are using the same standard population. Generally speaking, we use the WHO world population as a standard. Then we could perform the comparison across studies. And life expectancy at birth by gender is an intuitive index. Although it's not so scientific, but it's a well-accepted single indicator. And then the consideration, in the consideration of everything, we could get rid of the age structure issue. So we don't need to worry about the confounding from age. Okay? And generally speaking, it's given by gender, so we don't need to worry about the confounding from gender either. Okay? So we don't need to take care of the age and gender structure anyway. Okay. Ways to think life expectancy of our words. Here's a website which is very interesting because it summarizes everything about life expectancy at birth for countries all over the world. And the other good thing is that they split Taiwan and China. So for some cases, Taiwan will be blank or combined with China. Yeah, we don't really like that. We don't really appreciate that. Anyway, but it just tries to show what's going on by time, by place, by area or region in a very interesting way. You could even point to the country and get the curve about what's going on of the life expectancy at birth. Okay, so if we combine the gender together, it's over 80 in Taiwan in 2019. Okay, and in most of the countries in the world, in 2020, it's a little bit bending down because of COVID-19. Could be also caused by excess mortality because of crowded issue in the hospitals. In the hospitals because of COVID-19. Okay, that you could find a lot of interesting things. It's like changing over time. Before, in the year of 1800, it's all like that. And then become more and more brown or green because of the elongation of the life expectancy at birth. And also you can see the change over time and play it like a cartoon about what's going on, about life expectancy going up and up and up and up and up. See, the Asia is catching up. Africa is also catching up. So very interesting. So it's kind of something enjoyable. You could have fun yourself. I spend like hours I'm looking at it. Anyway, here's another example about how to apply the life expectancy as the indicator for the studies about the black-white life expectancy gap. Okay, so if you read through the abstract here, you find out, it makes much more sense because of my lecture for today. Okay? And also it could even give you very useful information about how to catch up or close up the gap. If we could focus on like the age of 55 to 69, and also if you focus on heart disease and cancer, then we could minimize the gap between different ethnicity groups. It makes a lot more sense, right, if you do understand what I'm talking about. And the other thing which is interesting is about the myth or argument that mortality rates and the causes among US physicians. A lot of people is talking about that don't try to be a physician because they live shorter because of stress, because they face people with disease every single day, right? So they make you depressed or this and that. Anyway, so people might say that the physicians got lower or shorter life expectancy compared to the general population. Is it true? I don't know, but we could check the evidence, right? So here's an article challenging the myth about that life expectancy at birth for the US physicians? The answer was not really. Okay, I'll tell you several different kind of reasons again, like the assignment. Okay, and the last one is a very interesting article published in the India journal. It's a letter to the editor, so it's kind of editorial thing. You could write a letter to the editor if they find it's interesting or makes sense. They will put it on there. It's arguing about the idea that the doctor here then they self addressing the shorter life expectancy of doctor in India. But in the first place, is it true that the doctors in India got a shorter life expectancy compared to the general population? So what you can do do exactly the same thing as what I did for the people with severe mental illness, right? We just follow up the group of doctors in India for a period of time, 1 year, 5 years, and do the calculation. Simply put the number into the Excel file, right? And we could get life expectancy at birth. And then we could compare to the national norm to make the conclusion, right? But this person or this scholar talked a lot of different kind of issues and things, but it did not really mention about the methodology or how he can generate or she can generate to make the conclusion with the idea or the concept about life expectancy at birth. Okay, and my explanation is that the answer will be pretty unlikely true that the physician got lower life expectancy compared to the general population. Why? Because who's the youngest doctor you ever seen in your life? Or at what age is the youngest one you ever met for physicians? Maybe 27, right? 27 could be the youngest one, right? And he or she, when he or she become a doctor, he or she has been escaped from the mortality, right? Yeah? So from age 0, the mortality rate for those groups has to be 0, or at least the same compared to the general population, till the age 27, and then they start to to experience different kind of things, right? Yeah? So how could it be possible, even if it's a little bit higher for the age-specific mortality rate afterwards, it's very unlikely to find out that the physician got much lower life expectancy compared to the general population, okay? And the Taiwan government did exactly the same thing and found out they actually live much longer than the general population. It's 86 or something, the life expectancy at birth for physicians in Taiwan. Okay, 86 compared to 81, much longer. Okay, so that's the lecture today. So you're welcome to look at those articles. They're very interesting discussion or debate. Okay, thank you.